Tonight's lecture is the third of 5 scheduled for this academic year in our Food for Thought lecture series. Now in its 4th year, this series focuses on biotechnology and related environmental, safety, and agricultural issues. Sponsors of this series include the American Society for Plant Biology, the Waite and Lois Rising Lectureship Fund from the OSU College of Agricultural Sciences, and the OSU College of Forestry. Dr. Savage obtained his bachelor's degree from Stanford University and a master's and PhD in plant pathology from the University of California at Davis. He's founding partner of the leading agribusiness consulting firm Cirrus Partners, where he is a specialist in agricultural biotechnology research and commercialization. His clients have included all of the major global technology companies, where he does in-depth analyses and advises on strategic technology options. His projects have included studies of synthetic and natural chemicals, biological controls, biotechnology, environmental toxicology, information technology, patents, biofuels, and climate change. As Steve Strauss and I were thinking about potential speakers this year, we realized we know of no other scientist with a comparable depth and breadth of knowledge in these many diverse agricultural technologies. Prior to creating Cirrus in 1996, Dr. Savage was a research scientist and product development manager at Mycogen Corporation in San Diego for about 8 years, where he worked on development of biologically produced pesticides and was awarded 2 patents. Before Mycogen, Stephen conducted and managed research at DuPont Corporation, was a professor at Colorado State University, and did postdoctoral research at the University of California at Davis. Tonight, Dr. Savage will speak not just on biotechnology, but on the broader environmental impacts of agriculture. He will discuss the pressing need to mitigate these impacts while also increasing productivity to support and reduce the environmental impacts of a rapidly growing world population. He will focus on the role of agriculture in causing and mitigating climate change, arguably the world's largest and most intractable problem of any kind. He will consider the role of traditional and alternative agricultural systems, such as organically certified products, and also the potential for new biotechnologies, such as genetic engineering, to provide useful tools for the enormous challenges we and our children face. The title of tonight's lecture is Agriculture 2.0, Farming Systems in an Age of Climate Change. Please help me in welcoming Dr. Stephen Savage to Oregon State University.
Thanks a lot, David. I appreciate your help in coordinating things, and I appreciate the invitation from Steve Strauss. And I'm very glad that you've come out and that you're interested in the future of food. It's something that I certainly agree is extremely important. The picture that we chose for the poster and for the opening of this seminar is a shot partly just because I like the picture. It's one that my son took on a trip to southern China. This is a place called the Dragon's Spine. And people have been terracing the hillsides in this area for about 800 years. And it's pretty amazing what they do. Some of these terraces are only wide enough to have 2 rows of rice in them. And they'll terrace slopes up to 45-degree angle. And I don't show this because it's in any way really a very good example of where we need to go with agriculture in the future. In fact, it's a little bit problematic from a climate change point of view because flooded agriculture like rice generates methane, which is a greenhouse gas on the order of 24 times as potent as carbon dioxide. So it's not really good from that point of view, but I do think that it's a beautiful example of both innovation and sort of making the best of what you have, and those are features of what we need to continue with in agriculture in the future. And I just hope that whatever we come up with can make as beautiful a picture as this. What I'm talking about tonight is not my own research. I haven't done my own research for a long time. I'm a consultant, right? But there's a great deal of excellent scholarship that's been done by lots of scientists. This is just sort of representative of some university networks, USDA networks. The climate-friendly farming is more of a Pacific Northwest network. These are people who have been for 1 or 2 decades doing the hard work of figuring out how does agriculture affect climate change and how can it do something about climate change. And so if you ever wanted to read more about this, the real science behind this, I would recommend these sources. Now, in 2007 and 2008, we experienced sort of a very nasty and unfamiliar event, which was a huge spike in commodity prices. Grain stores around the world had been driven down to very low levels, and all of a sudden prices went through the roof. There was a great deal of celebration and pickup truck buying in the agricultural community, but it was a real problem. In fact, there were food riots around the world as the actual acute shortages occurred, not the kind of politically driven things that we've seen over the past 20 or 30 years, but real live food shortages. And I think this was a bit of a wake-up call. How we got into that situation is an interesting story. And it turns out that some of the best news coverage that I saw of this was in the New York Times, which I didn't traditionally think of as a great source of agricultural information. But there are some writers there like Keith Bradsher and Andrew Martin and a lot of their associates who did a really good job of documenting how did we get into this situation where we had actual food shortages on a global basis. Most people just said, oh, well, this is about biofuels. This is, this is clearly what has put this thing over the edge. And there's no doubt that biofuels were a huge new customer for certain crops, and you can't have that without having some kind of impact. But it was probably overstated by most analysts. And the fact is, I never did find a single article that pointed out the fact that only 60% of the corn that goes into biofuel formation actually ends up in biofuels, and that 40% of it comes out as a thing called DDGS and is fed to animals. Even so, I'm not here to defend corn ethanol. I would never want that job, frankly. But there were several other factors, and I think it was a perfect storm in the sense that without all of these things together, we wouldn't have gotten to the situation we were in. Obviously, we always have the background of world population growth, which at best we're hoping levels off by mid-century. There was huge changes in food consumption as you were getting larger and larger middle classes in India and China in particular, and in other parts of Asia. Now, this is a good thing in the sense that if we have any hope of population leveling off, this is the kind of thing that's got to occur. But as people get a little bit more affluent, they change their diet. It puts higher demands on the world food supply. So this is definitely a major contributor to the situation. We had an energy crisis at the same time. Record oil prices, that certainly affects farmers, but it affects them also in the cost of fertilizers. There's a tendency to hold back a little bit on what you use. So that was part of the story. And finally, maybe the thing that was the tipping point is a major drought in Australia, affecting rice and wheat production from there, and that's a major exporting country. It really took all of these things together to get us to the problem that we had in 2007. Now, there's an old saying in agriculture that says the best cure for high commodity prices is high commodity prices. And certainly there was quite a response, particularly in crops like wheat. People planted it fence to fence and were able to drive that price right back down again. But it was helped a great deal by the fact that we've sunk into a global recession. I think, and a lot of other people think, that the fundamental issues that drove what we saw in 2007 are still going to be there and inevitably will come back if and when we recover from this recession. I don't think we're done with this. I think what we're done with is the period that we've seen pretty much for the last 30 years where, at least within the developed world, we almost have too much agricultural productivity. I think we're moving away from that paradigm probably permanently. So if that's true, and in the future we're going to need more food, not less food, there's only two ways to get that. You can farm more land, and I love that picture that was published in Time. I don't know why in the world somebody left this tiny little strip, but it's just a very gripping sort of view of what was going on there. So we can either do that, or we can produce more on every acre that we're growing. In an age of climate change, this is really not an option, and I wish there was a way to suddenly make that never be something that happens. Whenever you clear, whether it's a grassland or a forest like this, and turn it into agricultural land, first thing that you do is you liberate a huge amount of carbon that's been sequestered away there for decades until it reaches sort of an equilibrium. That's what happens within natural systems. And then in addition, you've added that much more area in which you're generating greenhouse gases to tend it as a farm. So this is really not the direction we want to go. If we need more food and we don't want people starving, we're going to have to do it by being more productive. Now, that's not unreasonable to think that we can do it, because if you look at the history of farming, we have been able to increase the production of many crops, particularly over the last 80 years. And that's come through a whole variety of different things, different changes in agriculture that have allowed it to be more and more productive. But the big question, and also we've done that at the same time as freeing up most of our workforce to do other things. But there are a lot of questions about, is this something that we can do in a way that's actually sustainable? Now, if you were to ask a great many people, well, what do you think we should do to have a more sustainable agriculture? They would probably say, oh, well, we probably need to do more organic farming. That I think would be a typical answer that you would get from a lot of people. And I'm going to say some things about organic here, and you might think, well, this guy is just anti-organic. I'm not anti-organic naturally. I mean, I first learned about the principles of organic from my grandfather in the 1960s, who was an avid reader of Organic Gardening magazine. Some of my best friends from my Davis days have been organic growers from that time. I've spent a substantial part of my career developing the kind of pest control tools that you're allowed to use within organic. So I'm not intrinsically against it, but the reality is that the vast majority of independent studies, and this is something coming out of DEFRA, this is something that was published in a Greenpeace article called Cool Farming, most of these studies show that organic agriculture is less productive on a per acre basis. There's sort of no way around that. So that's intrinsically kind of not a good thing if you're saying what I need to do is produce more on every acre of land. And there's exceptions to this, but in terms of the broad acre crops that really get the world fed, this is a major problem. The other thing is, and I continuously run into this, I get the clients that say, oh, I would like to develop a product for the organic market. And I say, you realize that the organic market is really, really small, because we've been hearing for 30 years that there's double-digit growth in organic. And there is, but that sort of implies that it's exponential growth. It's actually absolutely linear growth, and after 30 years, we're still only up to about 0.5% of American cropland that's inorganic. It's just not realistic to expect that this is ever going to be, in a time frame that matters to any of us, the way that you would feed the world. So the question is there a kind of agriculture that avoids the need for land use change, but is still sustainable? And the problem with the word sustainable is that there's about 6,000 definitions of what that means. For this evening's talk, I'll say sustainable from a climate change point of view, because that's something that's actually measurable, something that we can talk about, and frankly, it correlates extremely well with most other definitions. So that's the question. Is there that kind of agriculture? I'm saying that if there is, that would be sort of the agriculture 2.0 that I'd love to see us move towards. Step back and do a little background. What is the carbon footprint of agriculture? It's a very unique industry. As you know, whether it's a steel plant or a cement plant or a car manufacturer or something like that, it's mostly about carbon dioxide as sort of the master greenhouse gas. Ag is only a very tiny contributor to that. Maybe 2% of the, in the US, 2% of the CO2 comes from agriculture, which is pretty amazing when you consider the amount of land involved. But agriculture is a major contributor of two of the trace greenhouse gases. The first one being methane, which is like 24 times as potent as carbon dioxide as a greenhouse gas, and the other one being nitrous oxide, which is more than 300 times as potent as carbon dioxide as a greenhouse gas. Now, the way this graph is shown, those multipliers have already been included. So if you stack all those green bars together, you're only talking like 5 to 7% of US greenhouse gas emissions coming from agriculture. But that's really not an excuse to say, oh, well, it's only 5 to 7%. That's significant, and every industry needs to be doing what it can do. So ag is very unusual in what it does. And to really get down to individual farm and saying, well, where does the greenhouse gas emissions picture come on that farm, you've really got to look at the combination of 5 fluxes of greenhouse gases. First of all, you have the kind of straightforward one, which is the fuel that you're burning to drive your tractors around and your harvesters and trucks and all those sorts of things. That's pretty straightforward. There's also what people refer to as embedded carbon. This is the energy, fossil energy that was burned in order to manufacture some of the inputs that go into the agriculture. And so that's the fuel, the chemicals, even the manufacturing of the equipment. I can just tell you that the overwhelmingly large piece of that is for the fertilizer. Now, all soils tend to emit some nitrous oxide. And what happens is there are bacteria in the soil called nitrifying bacteria and denitrifying bacteria. And they change the forms of nitrogen that are available, nitrate, or ammonia to nitrate and nitrate to nitrogen gas. But in the process, the description is that it's sort of like a leaky pipe, and it's like they sort of accidentally make a little bit of nitrous oxide. And this happens when the soil is short on oxygen, okay? So it's kind of a random thing that occurs through the season. And typically, about 1% of the nitrogen that is applied to the ground as a fertilizer ends up going into the air as nitrous oxide. It's not a big deal in terms of farming point of view. It's 1% of the nitrogen. But with that 300 plus multiplier, from a carbon point of view, this is really significant. You'll see it's probably the biggest single challenge to ag. Agricultural soils, like all soils, will also oxidize a little of the methane that's floating around in the atmosphere. It's really tiny. I won't mention it anymore. The other really big part of it is the extremely unique thing about plants, which is that they grab carbon dioxide out of the air, turn it into organic molecules. Some of those end up below the ground, and a lot of that is metabolized and goes back up again, but some of it ends up in forms of carbon that are very long-lived. And actually, some of the ones that are longest lived are from the mycorrhizae that have been feeding off of the roots underground. And depending on how you farm, that flux of carbon into the soil can either be positive or negative. And so that's going to be a key part of how do you farm the right way in an age of climate change. So to understand how well a given farming system is doing in terms of climate change, what you really need to do is to look at this net carbon per unit of output. Because if you just say, well, I want to have the least carbon equivalents emitted per acre, essentially you would just say, well, the optimum is for me to do nothing on this ground. You're not going to get any food done that way. So what you want to do is say, well, how can I actually produce food, but make sure that the carbon footprint per bushel of grain or per ton of rice or whatever it is as small as possible. I'll use an example of what I call rational intensification. We're talking about the idea that, gee, we actually need to get more out of every acre that we're growing. Can we do that without making it worse from a climate point of view? So an example that I'll give is wheat in the eastern corn belt. This, which we've talked about today, is actually kind of an increasingly rare thing. But there's parts of the eastern corn belt, say in southern Indiana, northern Kentucky, where they do a thing called double cropping. They do a regular corn-soybean rotation like most of the Midwest does, but they're able to follow the corn with a winter wheat planting, grow that through the winter, and get it harvested soon enough to come in with the next bean crop. So they're able basically to kind of squeeze one more crop into the year. There's two basic strategies, and we did a project where we sat down at kitchen tables with growers and tried to understand their logic and how they would think about traits in the future and whatnot. But what we learned is there were two ways that farmers do this. One is a complete risk minimization strategy, and I would call that the low input. They just use some saved seed. They put on not that much nitrogen and just one shot in the fall. They use kind of old school seed treatment that's very, very cheap. And the idea is they just try to put as little money in it as possible because there are risks associated with this crop. And you could get winter kill, or you could get fusarium, a disease that kind of wipes you out in the spring. And so these guys have just risked the minimum. And if they get some wheat, that's great. And maybe that's going to be on the order of 60 bushel wheat, because this is a reasonably high rainfall area. Another alternative is what I'm calling intensive here. And this is not intensive by like European standards. All that we're saying here is that they're going to buy certified seed. So it's pure genetics, maybe a little bit newer variety. They're going to use a little bit higher seeding rate. They're going to do a split application, so they'll put on the fall nitrogen, but then they'll also come back in with some in the spring to sort of finish out the season. And they'll use a more modern seed treatment package and maybe one fungicide spray at flagleaf for disease control. That's about all they've changed. But mostly because they've added a little bit more nitrogen, you see that their footprint per acre has gone up. But because that takes you to about 100 bushels, the actual footprint per unit of output is down a little bit. But more importantly, you've sort of taken 40% off of your demand for land to grow wheat. This is the kind of thing that you need to do, but it needs to be evaluated this way to see if you're actually ahead both on the yield and on the carbon footprint per bushel. Now, as you'll notice in my description of getting a little bit more intense, I talked about at least 2 pesticides that were going to be used there. And I think it's worth sort of confronting this issue because I know that most people I talk to, and this is really true of most people I talk to in biotechnology as well, they sort of have this image of pesticides as, well, this is always something bad, this is always something you'd like to avoid. And so that's the question. Is it, pests are real, it's very much part of it. If you want to be very productive, you're going to have to do something about them. But is that automatically problematic? And in fact, this is only going to get worse as we are, in fact, moving into an age of climate change. All the models would predict that for California, we're going to get less of our precipitation as winter snows, which is a bad thing, but we're also going to get more of it as spring rains. Well, spring rains make good conditions for apple scab infection. And in fact, there have been several really bad apple scab years in California. Now, California is not that important to the apple industry, but it's the kind of change that you're going to be seeing. You know, I know a lot of people who just can't imagine that shifts of 1 degree or something like that mean anything. From a pest point of view, it can mean a lot. There's a pest called the potato tuber moth. Eggs get laid on tubers just before harvest, maybe through cracks in the soil and whatnot. And then during storage, these worms hatch out and make a mess of the potatoes. This has never really been a problem in the Pacific Northwest because this pest can't overwinter there. It now overwinters there. That's the kind of shifts that we're going to be seeing. So here's the question. Are pesticides as monolithically undesirable as we usually describe them as? To talk about that, we need to talk about toxicity. And I know this is only one dimension of the safety of a pesticide, but I could go on for 3 hours if we were to look into what the EPA really does as a risk analysis. But I think this is the thing that you can relate to the most, how poisonous, acutely poisonous is the pesticide. And to do that, I want to put that in the frame of reference of some more familiar chemicals, because of course everything is toxic at some level. Also, the way the EPA describes toxicity is in one of those things where it's called the oral ALD50, and it's, how much does it take to kill half the male rats? So that the more toxic something is, the number gets smaller. I find those kind of measures intrinsically ununderstandable. If it's going to be more toxic, I want it to be a great big number, okay? So I've made my own toxicity index where I simply take 500 divided by that oral ALD. And the 500 is convenient so that these categories down here that the EPA has, they call things relatively non-toxic, slightly toxic, moderately toxic, and highly toxic. It makes a 1 come right here at the border of moderately and slightly toxic. And as you look across there, a lot of things that I eat fall into that moderately toxic area. And I can imagine that, if I ate enough hot sauce, I suppose I could probably kill myself, but it would be hard. In fact, it would probably make you stop before you did it. But there are huge differences in the toxicity of products, natural products as well. Aflatoxin is out there just to show that there's a natural thing that you really don't want in the food supply that's made by a fungus. That's 1,000 on this scale. And then you see that there's things like vinegar or salt that basically are very, very low in toxicity. Well, let's compare these familiar things with a bunch of common insecticides. And yeah, there are some that are out there. These are 40 and 50-year-old insecticides, by the way, like aldicarb, which you probably would know as Temic, azanphosmethyl, which you'd know as glutathione. These are some pretty toxic things. And I think when most people hear the word pesticide, this is what they're thinking about. And these were the pesticides of the 1950s, okay? Now, they're still here. They're still being used in some very restricted ways. And a lot of people would love to see those go away, but they're only there because there are certain pests that are really difficult to manage. But I fully expect to see those go away completely in the near future. On the other hand, you see that there are a lot of insecticides that are less toxic than vinegar and salt. And in fact, the vast majority of fungicides and herbicides would fall into that range. Okay, but how much is in which category? That's kind of a key question. Took some data that one of my business partners, Greg Faust, had put together, had done a very nice job of tracking what particular insecticides are really getting used and how often in a bunch of fruit and vegetable crops. So this is fruit and vegetable crop insecticide use in 2007, okay? And we've got our same little cast of familiar calibration molecules up there on the top. And you can see that a very large proportion of what's getting used today is in this low toxicity range. And then over and above that, many of these things are being used at ounces per acre, whereas some of the old nasty things are being used at pounds per acre. So this is just one window into looking at it, and it's obviously a lot more complicated thing than that. I guess my only hope was to kind of give you the image that it isn't quite as simple as saying, gee, pesticides are bad or pesticides are good. There's a huge range out there, and it's very complicated. But I can tell you that if we had done this 20 years ago, those bars would have been shifted over that way quite a bit. There's been a lot of change during my career, I know that. So I think I already said the take-home points, but one of them is also that some of the products that are approved for use in organic are very low toxicity. There's one that was on there called spinosad. It's also extremely widely used in conventional agriculture. It's a fermentation product. It's very effective. But there are also some of the things approved for organic that kind of fall into that middle range. The copper fungicides that are used are not that, they're not dangerous, but they're not non-toxic like some of these other things. Okay, so let's get back to carbon footprint. I stole this from Davis. It's a nice graphic. I like that quite a bit. I went through and tried to calculate sort of typical carbon footprints for a bunch of crops, and did this based on publications that talk about what are the emissions from various procedures, and then lots of universities have very nice things saying, well, how much fuel gets used for tillage, how much, you can find pretty good records and come up with at least a reasonable picture of what's going on. And I don't want to get into too much detail here. Just one thing for perspective, if you look at the harvesting, which is sort of that brownish bar for processing tomatoes, that's burning like 37 gallons of diesel to run a tomato harvester over an acre. It's kind of a slow, heavy thing, and it takes some fuel to put that across. Just for perspective, that's more than the entire carbon footprint of farming an acre of wheat. Now, there's many millions of acres of wheat and corn, so what, in terms of where the real impact come from, you got to take that into account as well. But the one thing to notice right off is that there's two bars that are really quite dominant. That's the gray bar in the middle, which is fertilization, and that's mostly coming from the nitrogen. And then there's the black bar at the top, which is the nitrous oxide, which again is related to the fertilizer. So if you want to kind of step back and take one big take-home point, it's like, wow, fertilization is a big deal. So let's compare the carbon footprint of different kinds of fertilizer. Because I often hear the argument that says, well, if we weren't using synthetic fertilizers, we'd be a lot better off. But the reality is that every form of fertilizer has some embedded carbon in it. There's something in terms of greenhouse gases that are generated in the process of making this. For the synthetics, it's that in the process of making them, you burn, for the most part, natural gas, so that's a fossil fuel, so you've generated a certain amount of carbon. On the order of, like for urea, you're about 1 pound of carbon for every pound of nitrogen fertilizer that you get. So if you're putting 200 pounds of fertilizer, you got 200 pounds of carbon, which is a substantial carbon footprint. Ammonium nitrate, in addition to being a bomb ingredient, is worse because in the process there's some nitric acid and there tend to be some emissions of nitrous oxide, our big 300 plus greenhouse gas. So the worst of the synthetic nitrogens is ammonium nitrate. But in the process of handling manure to use it as a fertilizer, which you have to do because cows tend to make manure kind of on a daily basis, and farmers tend to use fertilizer on a seasonal basis. And so in the meantime, you've got a bunch of manure around. And even if you store it, according to the IPCC, kind of a typical range for what would be considered reasonable ways to handle the manure while you're waiting to use it, about 1.5% of the carbon in that manure is going to get turned into methane. It's just inevitable because there's these, well, they were in the cow to begin with, and anytime you get an anaerobic condition, which is going to happen in a big pile of manure, you're going to get some methane generated. That's not a lot. I mean, that's 1.5% of the biomass. It's not a big deal. I mean, you would think. And then if you are going to use that manure to fertilize, say, a fruit or vegetable crop, you really don't want to be using raw manure because you've got a lot of potential for E. coli contamination in that. So you need to compost it. And it was hard to find it, but there was a study by Howe et al. that really followed how much methane is generated from a commercial scale composting thing. I'm sure he had a graduate student do that, don't you think? I mean, anyway, and what he found is that in that operation, and that was a really good one, they turned that 5 times, and I think 3 is more typical. About 2.7% of the biomass got converted into methane. But remember, methane is more than 20 times as potent as a greenhouse gas. So if we look at this in terms of how many carbon equivalents would be generated to, say, make 100 pounds of nitrogen for a fertilization of a field, we have some really large numbers associated with the manure. Now, there is and could be a lively discussion about, well, whose carbon footprint is that? Is that the carbon footprint of the animal operation that generated the manure, or is that the carbon footprint for the farm that uses the manure? At some level, it really doesn't matter. If we wanted to change our agriculture into something that's going to be good for carbon, good for climate change, we really don't want to be using manure or composted manure, no matter who's to blame for the fact that the carbon is emitted. There's actually much better things to do with that manure. That would be to put it in an anaerobic digester, turn it all into methane, but then burn that methane to generate heat or electricity, so you've actually done something that's carbon neutral and you've displaced fossil fuels in the first place. It's a lot better solution than using it as a fertilizer. All right, so if there was enough manure to use for all of our crops, we wouldn't want to be using it anyway. And there isn't that much manure, fortunately. I don't think it would be a very nice world if there was that much manure. We should use anaerobic digesting, but now we're kind of stuck. We've got nitrogen fertilizer as this huge problem, this issue for agriculture in terms of reducing its footprint, and manure isn't our solution. So what are we going to do? Now, fortunately, there was a time where any increase in productivity pretty much was tied to an increase in nitrogen fertilization use. And that would have been true. Here we're plotting the bushels of corn per acre, which of course is always climbing. This is in Iowa. And up through about the mid-'80s, that was accompanied by ever-increasing use of nitrogen. But since that time, nitrogen levels have been static to even dropping slightly, because the gains that have been made have been mostly by breeding for plants' ability to tolerate higher plant density and for better pest control through a variety of things. So that's a little bit of an optimistic note to say, yes, we're going to keep pushing yields. It doesn't all have to be about using more nitrogen. But we're still got a lot of nitrogen. We still got a big footprint. We actually know a lot of things that we can do to optimize the rate at which fertilizer is used. But during an age of cheap energy costs, we also had cheap nitrogen. And so the way it really worked for a grower is that nitrogen was cheap insurance. If you just happened to, by chance, have a really great year, the last thing you wanted was to see your crop turning a little bit yellow because it actually needed or could have used more nitrogen than you gave it. The losses that you had on that side were much bigger than if you just happened to use a little bit extra. Now that's not a good thing, because the little bit extra tended to end up in the Mississippi River and out in the Gulf, causing a dead zone. So this all changes, at least partially, just once you shift the price of nitrogen up. All of a sudden, all these things that we know in that list over there that you can do to be really careful with your nitrogen application start to get implemented. But the goal of an agriculture 2.0, the way we really need to go, is to find ways to do that even more, with more focus than ever. And one of the ones, and it'll come up again, is to use a cover crop. Cover crop is in a temperate farming system where you finish the season and you've harvested the corn or the soybeans or whatever. Normally, what's been done is you either just till the field up or you sort of let it go to winter weeds or something like that. Cover crop is you say, no, I'm intentionally going to come in here and I'm going to plant, like a rye vetch mix or something like that. And depending on when you're able to get in and do that, you can actually put 50 to 100 pounds of biologically fixed nitrogen in that soil and have that much less that you need to put in the next year. These things can make a significant difference, and I think that's the direction that we'd have to go. Now that, after going through sort of the dark side of agriculture's carbon footprint, let's look at the upside. Again, this amazing thing that plants can do, which is to grab carbon and put it in the soil. But it isn't straightforward that that's the way it's really going to work. But it's what you want to do. You want to build up the organic matter in the soil. And if you ever meet a soil scientist, and they're very rare, but if you ever do, don't call it dirt. They really hate that. They get violent. What you need to do is think of soil as a living system. And it is. It's a very complex living ecosystem. And there's all these organisms down there that are dependent on the energy that's coming in through the plant. And the healthiest soils, the ones that are most productive, the ones that do the best job of capturing and retaining water and have the best ion exchange capacity, these are soils that have built up a lot of carbon in them. And really, you'd have to honestly say that it's organic agriculture that has maintained a focus on that during a period when a lot of the rest of agriculture kind of had the luxury of forgetting about it. I remember when my grandfather would be teaching me about his organic gardening techniques, he was almost totally focused on this idea of building up the carbon in the soil. That's really what organic was about until about 1989 when we had the Alar scare and it really started to become a big focus on pesticides. Well, and I would say that the way that organic has achieved building soil carbon is by growing that carbon someplace else, bringing it in, tilling it in large amounts, or by growing a green manure crop where you grow the crop, don't harvest anything from it, just incorporate all of that in the soil, or the cover crops that I've talked about. And cover crops were something that traditional agriculture did 60, 80, 100 years ago, typically. It's actually kind of rare in agriculture today. And so what's been happening is that we've been mining the carbon in our soils. And this is just one example. You can find lots of documentation that historically we started with soils that had pretty good soil carbon from the prairie or the forest or whatever had been there before, and we've just been mining it. Because when you till the soil and break up the soil structure, you expose these things to the ability to be metabolized, and your carbon goes away. Now, it turns out that there is another approach to building soil carbon, and it's something that, in a way, agriculture sort of backed into. That wasn't the original goal of what was going on. Back in the 70s, we had a big oil price spike. Some of us were here for that. And a lot of people said, well, we've got to do something to reduce fuel use because these fuel costs are killing us. And then people were obviously also concerned about soil compaction and about erosion. And so people started experimenting with the idea of, can you grow crops without ever actually tilling the ground up? And again, they were doing it for these fairly limited number of reasons. And in order to make that happen, they had to develop the ability to not sort of open a furrow and drop a seed into it, but make equipment that would sort of drill the seeds in individually, punch them right through the residue, as it were. To make this happen, since you weren't killing the weeds with discs and with harrows and things like that, you had to kill the weeds some other way, and selective herbicides were becoming available. And so that was a key part of it. Also, as you can imagine, that tilled up soil is a lot darker, and it's going to warm up faster in the spring, and the untilled soil is going to warm up slower. So you had to both look at the genetics and its seed treatments to kind of help the plants get going in actually a little bit more difficult situation. But people worked this out, and it actually was successful. They discovered a bunch of other advantages to this that weren't necessarily part of the original plan. One of which is that when you farm this way, instead of always mining the soil carbon, you actually start building it up again. And that makes sense in a way, because how does soil carbon build up in a natural setting? Well, people don't till manure into natural settings. It's just plants that grow, the roots feed things underground, the debris falls on the top. That's the way natural soils are built. Why couldn't it work something like that in an agricultural system? The other thing they found is that by not disturbing the ground and by having something to block evaporation, they were able to actually grow crops in much droughtier areas than they had been before. You can just watch how no-till adoption allowed corn and soybeans and things like that to move west. And they also found that there were some operational efficiencies, and that's not a bad thing. Remember that plot of how many people work in agriculture? It takes less time to farm this way. And so an individual farmer can farm a bigger area. And no-till has actually achieved a lot of adoption. Nobody's paid anybody any special thing to do no-till, anything like that. But there was adoption of it because it actually made operational sense for the farmers. And the government stopped tracking it in 2005, which is too bad. But at least by then, we're up to more than 60 million acres. Now there's at least 200 million more acres that you would like to see go into no-till. So let's look at a no-till scenario back to our Indiana wheat farmer. In this case, he's going to do the intensive, but he's going to do it no-till. So you notice that the fuel cost for the tillage goes away. The herbicides that he's using here are actually a little bit lower use rate. And so that little red chemical bar, which isn't very big, shrinks a little bit. We've got the same nitrogen input, but now this crop is plugging away more than 300 pounds of carbon per acre in a year. And if you do that, essentially you've eliminated the carbon footprint of farming it, and yet you've still achieved your 40% reduction in land use demand. This is really the sort of scenario that we'd like to move to for a lot of crops. So in Ag 2.0, how are we going to build soil carbon? It really needs to be more than just avoiding tillage. I mean, no-till is great, but if you really want to get serious about building soil carbon, you need to do more than that. And part of that involves how you actually manage the residues, and a big part of it has to do with whether you plant cover crops. That's sort of the thing that isn't happening broadly now. There are definitely innovative farmers out there that are doing all three of these kind of in an optimal way, and they're seeing some really big benefits. There's climate benefits directly, like using less fuel. There's the potential for farmers to actually be paid in carbon offsets. If we set up a cap and trade system in carbon, which is more likely now than it was a year ago, and if we can work out a system where the carbon is, we can be sure that the farmer that's getting paid is really doing it in such a way that he's sequestering carbon, then there could be a source of money to help the grower do what would be best in the first place. Over time, you can limit N2O emissions, and part of that is just that cover crop. A cover crop that comes in and scavenges up the leftover nitrate at the end of the season helps a great deal with eliminating nitrous oxide emissions. And then we can also do nitrogen fixation biologically and offset part of the need to put synthetic nitrogen on. But we also get benefits for erosion, soil compaction, nitrate leaching, pesticide leaching. There's a huge increase in biodiversity in an undisturbed soil. And there's a huge increase if you keep feeding the soil. You know, if you just do a corn-soybean rotation, you've only got a few weeks of the year where you've really got a plant pumping some carbon down there. You need to have something there most of the year to keep those bugs fed. There's also the possibility, people have worked on cover crops that do a good job of suppressing nematodes, for instance. I mean, if you're going to take the trouble to go out there and plant another crop, why not use that as a platform for additional things? But the really big deal is that, and this doesn't happen early, you've got to get to the point where you've really restored that carbon back up to sort of where it should be. You start getting soils that are really good at capturing rainfall and at retaining that rainfall. And it's almost as if you've given yourself several inches more of rain. And there's a lot of anecdotal evidence where somebody who's been doing this for quite a while can be getting substantial yields in dry years where his neighbors are getting nothing. And how big a deal would that be? That would be a really big deal. This is a plot, normalized county-level corn yields from 1996 to 2006. So this is about 18,000 data points. And the reason to put this here, obviously, precipitation is what it's plotted against, and that has an influence, but obviously a lot of other factors are involved there. But at the very least, you can say there are a heck of a lot of counties in a heck of a lot of years where you're getting less rainfall than you would ideally want. And if you do this change in the soil, it's almost like you're shifting the x-axis over, and you're getting more yields than you would have gotten. So, sort of in conclusion, what we want, if we're going to farm the way we should farm in an age of climate change, is we've got to get the productivity we need without adding more land. We need to really work seriously on optimizing our nitrogen use and to minimize our emissions of nitrous oxide. And we need to make a concerted effort to really do a good job of sequestering carbon in the soil. Now I'm going to go through a little evaluation of different farming systems and say, well, how well do they do with regard to these three basic goals of productivity, nitrogen management, carbon management. I'm going to look at sort of Ag 1.0, sort of mainline conventional agriculture in the United States, the same thing in the European Union, organic as a system, and then sort of our imagined Ag 2.0. From the productivity side, all of these systems have access to elite genetics. So that shouldn't be a problem, and those are extremely important component, and a lot of people that work here are working on that exactly. In terms of being able to do pest control, in terms of chemical sprays, most of the systems are in good shape. Organic has a few good tools. I can say as somebody who spent years developing some of the tools that they have, a lot of them aren't really as potent as you might like them to be, and they're tricky to use. That's part of the reason that organic yields are lower. In terms of pest control through traits, something like Bt corn, something along those lines, the European Union has, for the most part, opted out of that, so they don't have access to that. And then traits which are just beginning to emerge now in terms of stress tolerance, salt tolerance, cold tolerance, nitrogen use efficiency, things like that. Only Ag 1.0 and Ag 2.0 sort of have access to that technology. In terms of the fertilizer footprint, I'd throw that into the non-ideal category for all Ag 1.0. And Ag 2.0 only gets up to sort of good because we haven't solved the whole thing. If you can come up with a way to biologically fix nitrogen in a tank and then be able to put that out on a field, you deserve a Nobel Prize like the guys got for synthetic nitrogen in the first place. Again, because of that methane issue, fertilization is problematic from an organic point of view. And then in terms of building soil carbon, here's where organic, again, it shines, but it's a different approach. This has been really a problematic aspect of traditional agriculture. In terms of no-till adoption, which is also part of the story, that really it's been good for the part of traditional agriculture that's adopted it, but there's a lot that haven't. And no-till isn't something that you can really do in an organic system because you don't have any herbicides. Also, if you're fertilizing with something like manure, you have to till it in. You don't really have the option to a great degree of doing that without incorporation. Now, what's going to make this actually happen? Because it's very nice for me to talk about what they're ideally. Growers are businessmen. They're going to do what actually works and what pays the bills. Growers that aren't good businessmen aren't growers very long. Okay? So what's going to make this happen? There's actually several things that could come together to make this happen, and that's why I have any optimism about this at all. I mean, first of all, basically, if you go this direction, there are grower benefits. It's just that some of them take a fairly substantial investment. They take, to buy a no-till planter costs you money. To wait for that yield benefit from drought, that's several years. That's kind of hard to do if you're renting land, like 40% of the ag land is rented. Actually, some renters are starting to put clauses in their rental agreements that require no-till, for instance. But it's going to be hard to get there if this is all on the back of the grower. That's why the possibility of carbon markets would really help. If carbon trades at $30 to $50 a ton, and you're putting on the order of 300 pounds per acre into the soil, that actually begins to add up. And that could sort of make the difference. Can that grower afford to buy the cover crop seed, that sort of thing. Also, there are a lot of food companies that are concerned about wanting to be out ahead of trends in terms of sustainability. And some of them have made sort of sustainability promises that are actually a little bit goofy because they didn't get a lot of good advice about what was actually sustainable. But it's interesting that there are several that have started to say, well, we're going to do things that make sense from a carbon point of view. And these are two divisions of Frito-Lay that in one about a year ago with Walker's Crisps is Frito-Lay or potato chips in England. And then just like a week ago, Tropicana came out saying that they were going to publish carbon footprint information on their labels. Now, at first, this is going to be completely non-contextual for the consumer. It's like, well, what does that mean? You know, this says that there's 75 grams of carbon embedded in this bag of potato chips. What does that mean? But eventually, you can have people learn to say, well, this is lower than this one. I mean, initially, I think probably the idea is that people just say, oh, well, it must be good if they're willing to talk about it. But what's fascinating is that then on the website for the company, there's a pie chart like that that says, well, where did the carbon that's in those potato chips come from? And notice that, if you can read it from here, farming is the yellow. It's the biggest part. Well, what if we were able to do something in the way that you farmed the potatoes that actually substantially reduced that footprint? Then they'd be able to have the bragging rights to say. So you can't underestimate the leverage that a retailer or a food manufacturer has in the food chain. There's very few of them, and there's a heck of a lot of growers. So when they say, we want this done this way, and we're going to buy from people who do that, things happen. If we're going to do government supports for agriculture, and I guess if you get secretaries of agriculture from Iowa, you're probably going to continue doing that, you should at least make those contingent on particularly beneficial practices. Actually, you're not in violation of World Trade Agreement sort of issues if you make them into green payments instead of just straight subsidies. And I'm not a big fan of subsidies in general, but if you're going to do it, say, well, we're going to do that to invest in the soil carbon of our country, because we know that that will lead to greater yield and greater yield stability in the future. That would make a certain amount of sense. So here's just some of the components, some of the major components of this Ag 2.0 vision. And the last point I want to make, this isn't just an extension of any one existing system or contributor to agriculture. If you look at really safe pesticides, nitrification inhibitors, which is one of the things that can reduce nitrous oxide, and best genetics, you'd really need to credit a lot of that to sort of conventional agriculture. But you can credit organic agriculture also with some of the safest pesticides that are out there, and sort of the being there as sort of a driver to sort of force people in that direction. And again, I would credit organic for sort of maintaining the flag there on the whole idea of cover crops, which are a really good idea. And there's been sort of a progressive wing of Agriculture 1.0. There's people that are into precision ag, and these are the people who do things like site-specific fertilization for different parts of the field, getting different fertilization based on the yield history of that field, things like that. And these are the people who really pioneered the no-till. Okay. And then biotechnology has come in. It has generated some traits, and traits are great, but they will never do the whole thing. You know, first of all, there's sort of a threshold of investment that the final opportunity has to be pretty huge to invest the money that it takes to go through the whole scientific and regulatory process for a trait. But for the big crops and the places where it makes sense, that's been a big contribution. Biotechnology is also making a substantial contribution now just by making regular breeding far more efficient. When you look at marker-assisted breeding and what that's doing and how that's accelerating the improvement of crops, and this is in a non-transgenic way, it's just understanding what genes you're moving around instead of just looking at how the plant looks. So really, Ag 2.0 is an evolution from several different paths if combined properly. So I don't know if it's going to generate things that actually become tourist destinations to take pictures of agriculture. Maybe it will in certain places. But I hope that it would be an example of the same kind of innovation, the same kind of concentration on getting things right.